Metals are the basic material of industry. Steel is the most used because it is strong, can be shaped, and is cheap. But when the air is moist, it will corrode. And will corrode even more quickly when the atmosphere is polluted. But corrosion can be controlled by keeping out the atmosphere, and a barrier can be provided in different ways. Firstly, steel can be coated with another metal which corrodes more slowly. This can be done by dipping in a bath of molten metal, or by spraying on a metal layer, or electrodepositing layers of more resistant metals. Secondly, a non-metallic barrier can keep out the environment completely, as for example with a thick coating of rubber or plastics. Thirdly, a barrier can control the environment on the steel. A film of paint, while not completely impervious to moisture, can greatly reduce corrosion of the metal. And occasionally, as in some river piling, it may be cheaper to use thicker steel and just let it corrode. The choice of barrier depends upon the environment and the cost. From the moment steel is made, corrosion begins. Oxidation forms mill scale on hot steel, which has to be scraped off and blasted with jets of water before the steel is rolled into shape. Steel will corrode further in transit and storage. And ideally, it's given a primary protection. The surface is blast cleaned on both sides, back to bare metal. A priming coat of paint is immediately put on both top and bottom to give protection until the steel is used. If it's not being shop primed, even new steel will need proper cleaning before a protective coating is put on. For structures in the open, wire brushing is inadequate because it only takes off loose rust and still leaves contaminants. Much more effective is blasting with grit particles, either in the shop or on site. Blasting can also give the appropriate surface profile for the coating to be used. Even better is using both grit and clean water, which effectively removes rust and washes away soluble contaminants. Pickling in acid is common in the factory. Crevices and narrow sections are cleaned, but afterwards the components may have to be washed and dried. Preparation of the surface may be costly, but a coating is only as good as its foundation. Steel may be protected with a more resistant metal by dipping in molten zinc or sometimes aluminium. Hot dipping gives firm adhesion because of the metallurgical bond of the zinc and steel. Contours and interiors can be coated evenly. Galvanized coatings are resistant to abrasion and will cathodically protect steel at cut edges and areas of damage. Zinc or aluminium can also be applied as a metal spray, melted by a gas flame or electric arc. The molten droplets adhere well to a blast-clean surface, and thick coatings can be built up even on site. The other method of applying a more resistant metal is by electroplating, with layers of copper, nickel or chromium, for example. Because it's expensive, plating is mainly used for components which are small and need a decorative finish. An advantage of plating is that the thickness can be controlled. However, these metals do not protect at cut edges or areas of damage, and the coating must be free from pinholes. When tin is applied to steel electrolytically, the coating is then flow melted, which gives a firmer metallurgical bond and a non-porous finish. Tin-plated steel is widely used in containers for food and drink, for its corrosion resistance. In a different electrochemical process, a protective coating can be built up on aluminium. Anodizing in sulfuric acid solution forms aluminium oxide, which gives a resistant film. This can be dyed in a range of colors. Although more expensive than steel, anodized aluminium can remain corrosion-free for long periods. The second method of controlling corrosion is to keep out the environment by coating with a thick layer of plastic or rubber or vitreous enamel. As well as being applied by dipping in liquid, heated steel components can be coated in a fluidized bed of powdered plastic. Cooling in water hardens the plastic. Where a thinner coating is tolerable, powders can be applied by continuous production methods. For example, car components are cleaned and then dried with hot air. The sprayed powder is electrostatically charged so that it attaches to the metal parts. The conveyor then runs through a heated chamber, where the plastic softens and adheres to the steel to form an impervious coating. Steel strip, coated with plastic on one or both sides, is produced in considerable quantity. It's commonly used for cladding. All the coatings seen so far are best applied under factory conditions and cannot easily be maintained on site. Ease of application is one big advantage of the third method of preventing corrosion. Paint comes in a vast range of colors, but decoration is only one function. In addition to coloring pigments, there are others which control the environment at the metal surface. Basically, paint is a liquid called a binder, which dries to leave a protective coating. This coating acts as a filter, passing uncharged molecules such as oxygen and water, but excluding charged ions of aggressive chemicals which would corrode the steel. Nearly all paint films are permeable to some extent, and how much goes through depends upon the temperature and film thickness. The unpainted surface of the steel will quickly become contaminated, and unless properly cleaned, corrosion would be inevitable beneath the paint coating. This would then fail. So pigments are added to the binder in some priming paints, which control the conditions on the metal surface. Chromates in paint act in this way. And the compound formed from red lead in linseed oil. The inside of one beaker was coated with linseed oil and red lead, and another with linseed oil and iron oxide. After drying for a few days, each is filled with distilled water, which penetrates the linseed oil film. A clean steel plate is put in each beaker. After a week, the plate in the iron oxide and linseed oil has rusted. But the red lead and linseed oil has formed an active compound which has leached into the water to prevent corrosion. Corrosion has been controlled by chemical action. To increase the strength of a paint film and reduce its permeability, flaky materials such as micaceous iron oxide or glass are added. And these, seen under the microscope, are lying together and protect like slates on a roof. Similarly, paint containing sufficient zinc dust may protect steel cathodically. However, a single coating of paint will rarely give all the necessary protection, and so it's common to use several different layers. Steel must first be cleaned. Then a priming coat will ensure good adhesion and control corrosion. Layers of undercoat build up the thickness to reduce penetration of water and oxygen and give strength. Finally, the paint system is finished with a top coat, which carries the colour and gives a surface resistant to wear and ultraviolet light. In practice, there are many paint systems for differing environments, and the choice will need expert advice. But whatever paints are used to control corrosion, application must be correct at each stage, and this needs inspection. Thorough cleaning is the first essential, because there will be small particles of aggressive salts under the surface rust which would cause corrosion and damage the paint film. Blast cleaning should remove rust and contaminants. Quality of the metal grit needs maintaining, as it closely affects the surface profile. Peaks left on the surface, which are higher than the thickness of the paint, will stand out like rocks in the sea, and then only have a thin covering of paint. One method of evaluating the profile is to smooth on a piece of plastic which reproduces the surface. Inspection, too, can determine whether ferrous salt contaminants have been removed by testing with paper impregnated with ferrocyanide. Here, further cleaning is needed. The surface must be free from dust, which will affect adhesion. From the temperature of the metal and the relative humidity can be calculated whether condensation will occur, which would also reduce adhesion of the paint film. As well as shop painting, maintenance painting particularly needs inspection at each stage. For major repainting, grit blasting back to clean metal is necessary for all rusted areas. The thickness of each coat of paint should be checked to ensure that protection is adequate. And of course, the surface must be free from condensation. Recorded inspection data allows analysis of subsequent performance. If dry weather is uncertain, then temporary protection must be erected. At this plant, the temporary coverings are enormous. Of course, it's preferable to carry out maintenance in the shop, where conditions can be controlled. What cannot be covered has to be painted when the weather is fine. Rusted areas are cleaned and coated with primer. This is then covered with finishing coats. Sometimes the cost lies not so much in labour and materials as in the time travelling between each site. And of course, another expensive item is the erection of scaffolding, even for maintaining a few window frames, pipes and gutters. Or the cost of the scaffolding and covering may be by far the largest item, other than loss and plant shutdown. So, maintenance involves a number of factors, which can all affect the cost. It often means disruption of the site, usually for some time. Let's say this is 15% of the cost. Scaffolding will be needed, and this is not cheap to erect. Blast cleaning of the steel surface will add a further 20%. Labour for painting would come to another 20%. The cost of materials, 3 coats of paint, would come to about 10%. Both preparation and application need supervision and inspection, which will cost about 5%. Usually the cost of the paint is only a small part of the total, and it's worth using the best materials. Because it is used in extreme conditions, avoiding corrosion in the car is neither easy nor cheap, but it can be done if cost is not all important. The body has been phosphate coated to improve adhesion and then washed. After drying, it's coated with a primer, which carries zinc chromate to control corrosion. Each body is completely immersed in a further waterborne primer. Some processes use electrophoresis to improve the paint distribution. This primer provides a good base for the more resistant coatings to follow. It's dried in a heated oven. After inspection, the body joints are sealed with a mastic compound to prevent crevice corrosion. Then 2 further coats of paint are given, and again each coating is cured by heating in an oven. These layers build up a thickening to reduce the penetration of contaminants. More than 3 kilograms per square metre of underseal is applied to resist abrasion. Further coats and rubbing down don't affect corrosion resistance, but provide the base for the finishing layers. Eventually, 4 colour coats will be applied and stoved to give a hard, decorative surface. The useful life of any coating will depend upon its thickness and continuity, and the preparation of the metal surface. Prevention of corrosion by coating depends upon the environment and the original design and purpose.